Okay. Okay, welcome to the next session. So we have the final lecture by Henrik on double copy.
All right, thank you. So yesterday and the day before, I was basically going through color-kinematics duality at tree level, and also introduced the first version of the double copy. And what I'm going to do right now is I'm going to generalize what I did last time to loop level. And it's going to go really quickly. There's not so many things different at loop level compared to tree level. I mean, of course, it's maybe more complicated in practice, but in terms conceptually, it's not so different. And then after that, I'm going to talk more about KLT, which you already heard a little bit about. But let's do loop first. Okay, so loop level, color-kinematics duality, and double copy. So let me just write up the two formulas. So one formula for gauge theory at L loops. So we're going to write it now as some integral of some loop momentum. We're going to have some dimension d, and we're going to have L loops, and there's also some 2 pi, which is just convention. Then I'm going to write a sum over diagrams again. So cubic graphs. And yeah, so we have the usual color factor, we have numerator factor. Maybe I can indicate that numerator factor depend on L, and here L can be any number of loop momenta. And we have the denominator here, which also is a function of L, but it's a trivial, well, it's known what it should be. Just all cubic graphs in some appropriate labeling scheme. So one thing that does change a little bit at loop level is that you have to be careful and also include a combinatorial symmetry factor. So there's a symmetry factor here, which basically mods out by overcounts. So if you happen to overcount your graphs, you have to mod out by that. So there's the usual symmetry factors that you always find in Feynman rules. For example, if you have a bubble graph, you should divide by 2, just so you don't overcount the phase space of the bubble. But otherwise, yes, let me say this is a symmetry factor. And it's completely standard, it's present in any Feynman rules. And it essentially mods out by the graph automorphisms, so this is related to graph. Right. So if a graph has some automorphism symmetry, meaning that you can map it to itself, you should probably mod out by that, because otherwise you're overcounting. Either you're overcounting permutations or you're overcounting phase space in your integral, for example. Yeah, and let me write right away the corresponding double copy formula before I say anything more. So there's a double copy formula at L loops, and again the prescription is just to write down the same thing here as in the gauge theory. Same sum here, same symmetry factor, and now you replace one of the color factors with an additional numerator factor, and I twiddle, and you have the same denominator. Yeah, and one thing I didn't say very much, well, I didn't say it at all, last 2 lectures, is that in principle you can also consider massive series, and then there would be a mass in the denominator. You would have something like p squared minus m squared for each graph denominators. If you have a massive line, you know, the numerators can also depend on mass and so on. But yeah, that's not something I'm going to cover in any detail, so there could be massive denominators. And then, okay, so the reason I'm saying that is that it's important that you match whatever this denominator factor here, it should be the same as here, graph by graph. All right. Right, so in order to have color kinematics duality, the numerator has to satisfy Jacobi relation, kinematic Jacobi relations. And so, but what's very important, and which sometimes is overlooked, is that the numerators ni or ni triddle has to satisfy Jacobi relations at the integrand level. Right, so it's very important that it's integrand because there are functions of L, so you cannot consider Jacobi relations after having integrated. Now, those of you who know anything about non-planar Feynman or non-planar amplitudes knows that the notion of an integrand in a non-planar amplitude is somewhat tricky. So what I really mean here is that you have to consider the integrand on each cut and make sure that the Jacobi relations hold on the cut. So yeah, so this is well defined. For each cut. So what I mean here is that you find some global functions which are these numerators, and then you map those functions onto a cut in a particular way by summing over the graphs that contributes to that cut. And on that cut, you have to make sure that they obey the same rules as the numerators did at tree level, so all the Jacobi relations subject to that cut. Now you don't really have to implement this, cut by cut. You can just implement that fully off shell, and then it's guaranteed that it's going to work when you map it to a cut. But essentially, that's what I mean. That things has to, you do your relations such that when you do the cut, they still work in the usual way as they work at tree level. Yeah.
By cut, you mean maximum cut?
Any cut. Each cut, maybe I should say physical cut. And the only reason I specify physical here is that, well, there are some cuts which diverge. For example, if you do a planar cut and you a single particle cut where you sew together two adjacent legs in a non-supersymmetric theory, for example, like QCD or Yang-Mills, it can diverge. So I mean, you just do the cuts, which are sufficient to get all the discontinuities in your amplitude. And this is people who do unitarity method knows which cuts to consider and which cuts you can ignore and so on. But yeah, so for example, if you do n equals 4 sup Yang-Mills, you can pretty much do any cut. They're well defined. There's no singularities, but sometimes you have some collinear or soft singularities that just forced upon you by your kinematic. And if they're divergent, you can typically ignore this because it's the error that you make are just gonna correspond to contributions that integrate to 0 in dim reg, so you can ignore it, I guess. Right, but typically it should work on any cut. And yeah, I'm not gonna say more about how to practically implement it. My point here was just, you have to do it as functions of L. which basically means that you're working at the integrand level. Now, another subtlety here is that color factors should not be explicitly evaluated. Of course, if you only care about the Young-Mills amplitude, you can do it. But if you care about replacing your color factor with the numerator, you have to be a bit careful. And the reason is exactly the same as here, right? That when I say about evaluating a color factor, it's very similar to evaluating a Feynman diagram by integrating it, right? And you know, things might disappear when you integrate. Things might vanish. There's integral that vanish, but and similar that there are color factors that actually vanish when you evaluate them. So one very interesting example of a color factor that actually vanish when you evaluate it is this for loop. It's a for loop non-planar diagram at 4 point. If you actually evaluate it, it's 0. So the color factor of this diagram is 0 in any gauge theory. Any gauge theory where you address the vertices of FABC. And the reason for that is that you can check that this diagram has automorphism symmetries, which on the one hand says that it has to be equal to itself. On the other hand, it says it has to be equal to negative itself. So the solution to that is that it's 0. But nevertheless, the numerator is not 0. And if you do a construction of this numerator, as we have actually done in the past, the double copy of it is also non-zero. So that's why you have to be careful and not evaluate. So by evaluating, essentially what I mean is actually explicitly summing over the internal colors. Right, so you have to, which is pretty much the same as integrating over the internal momenta, right? So you have to work at the summand, just like you work at the integrand level, you have to work at the summand level, and just consider it to be, you know, more or less an object where you have not yet done the full color sum. All right, any questions about that? Yeah, so the last subtlety here at loop level is that I didn't say explicitly what is this sum run over here. What the sum runs over depends on how you're doing things. It's something we don't maybe think about very often, but in principle, it's not clear that this sum is finite. So the way to get it to be finite is to impose graph automorphism identities. So you have to impose identities on the numerators. To be, you know, in order finite number of graphs. It's not so obvious why that's the case, but it turns out that if you if you do all Jacobis that you can imagine, it never ends. There's an infinite number of Jacobis, and the reason is because you, in principle, there's many different ways of labeling your diagram, and labelings will differ by some shift of the loop momentum by the external momenta, and in principle, all of those numerators are generated when you do Jacobi relations, and in order to remove such numerators, you have to map them back to some canonical labeling, and that means that you have to have some automorphism such that you can do the map. So for example, at one loop, we have this diagram, and for example, a typical labeling is that we call this loop leg L here. Now this diagram is really the same thing as this diagram, where I call this one L prime. It's obviously the same diagram, I just used a different L. And so I might call this numerator N1, 2, 3 to N, which is just denoting the external labeling. And then I call the loop momentum L here. But this has to be equal to N1, 2, 3, N, L prime. And L prime is in my outgoing convention. I guess maybe it's different than what Jaroslav picked, but so this is L minus P1. So this is an example of a graph automorphism identity that I implemented on my numerators, right? Because the problem is that I can use Jacobi relations to move a leg around. I can commute it past leg 2. I also generate another diagram which has a fork, but let's ignore that. I'm going to generate the same n-gon, and I can move it all the way around over here, and that's basically what I have here, that I have moved leg 1 all the way around. And so clearly Jacobi relations will generate such numerators, so I have to know how to relate them, and that I do by imposing graph automorphism identities. And usually we don't think about this because that's trivial from Feynman rules. Like any kind of Feynman rules that you use will have this property, so it's not something we think about very often. People who use unitarity method also typically implements this, but it's so obvious to people who do unitarity method that we usually don't think about it. But here we really have to think about it because we have to solve some system of equations, and these are functional equations. And the problem is that if we get functional equations with shifted arguments, which we did here, it's not very easy to solve them. All right. And I think this is actually related to some of the stuff that Nima will talk about. I assume he's coming, so he will. Well, I heard a talk from him in Munich, and he was actually talking about how to consider phi cube diagrams and relax this condition here, right? So he actually have an infinite sum of graphs in his representation. Anyhow, not going to say more about that. Is there any question about loops? Because I think I said everything I wanted to say about loops. Essentially, loops is conceptually trivial. You just add an integral. Yeah. Questions? Maybe you? Yeah.
So let's say you double copy
Yeah. Well, so one condition here is that you have to match graphs such that the propagator is the same, right? So for example, if you have, I mean, here it's obvious that this sum here runs over some graph topologies, So we're matching the topology with topology. But you can also say, well, what if you have two equal topologies, but one of them is maybe some massive fermion or whatever, and one of them is a massless gluon, right? Like if you have these two box diagram, one of them is massive, the other one is massless, you should definitely consider them to be distinct diagrams. So this index here is running over these two diagrams, and they're distinct, right? Yeah. So that's a necessary. So you have to make sure that the denominator is the same. Otherwise, it doesn't make sense. Yeah, Lance.
So if you're going to move on from loops, I just wanted to ask, what do you do with the loop diagram once you have it?
Well, I mean, what we had done in many papers was to actually extract the UV divergence, because that's something which is relatively easy to do at high loop orders. At some lower loops, like 2 loops, 5 point, we just hand it off to somebody who can do the integrals, like Lance. But often, I mean, there's not too many things you can ask. I mean, well, gravitational amplitudes, what are they useful for, right? I mean, they're not useful for very much things, especially not when they're massless, because we cannot observe massless, graviton scattering. So the only two uses is, well, you study the UV properties or you study their analytic properties. Is there some interesting cancellations that happen when you have n equals 8 supersymmetry or whatever, right? So, yeah. Yeah, you can generalize this to classical scattering of massive compact objects. If you have a low enough spin, spin is a bit too high, there's some problems maybe, or potential problems. I'm not going to cover it because I assume Svi is going to talk about that. Or maybe when Svi comes here, he's going to claim that I already covered it, so he can skip it. Yeah. Anyhow, I think there was some other questions, so yeah.
I was wondering, do you have any intuitive reason why this works a level of integrals? Because it looks like still at 3 level.
Yeah. No, exactly. I mean, as I said, it's almost conceptually trivial, but in practice it's very complicated when you actually do it. But conceptually, it's just the idea that we have a general property working at 3 level. So we just try to lift it to loop level via unitarity method, right? So, which I didn't say. So basically, we know that unitarity method expresses loop level quantities in terms of trees, because we can sew together 3 level amplitudes to get unitarity cuts, right? So we know that, if we can implement some property like Jacobi relations at 3 level, we surely should be able to implement it in cuts, right? Now the difficulty with promoting cuts to loop amplitude is that you have to have some internal consistency between different cuts, right? So that's one of the challenges. So it's not enough to just do one cut, find your numerators, and then you're done, right? You have to make sure that all cuts, which might be overlapping in many different ways, all of them has to work. And the way that we solve that is basically we say that there's a global labeling, or there's a global set of numerator that, independent on whether you do this cut or that cut, you should use the same numerator, up to graph isomorphism. So typically you're not allowed to have multiple versions of the same graph, depending on which cuts they contribute. It has to be the same numerator, right? And so that's basically, so we implement Jacobi relations globally, meaning that we find these functions n of L, and then when we check cuts, we check that, that choice was consistent on this cut, it was consistent on this other cut, and so on, right? And that's typically how, unitarity method has been implemented at higher loop level always, especially when you do non-planar diagrams. I mean, it's basically the only way to do it. You give a set of diagrams, and then you say that, yes, we check that when you feed them into a unitarity cut, it matches the product of tree-level amplitudes. So it's not, that, you know, that part is not different. Yeah. Oh, you might wonder, how do we do this in practice? Well, how do we do? Well, we just write down an ansatz for these functions. So we assume that they're polynomial. And if they're polynomial, you know, there's a finite ansatz. And that works in many cases. Sometimes it does not work. But the cases where it doesn't work, it's just because the ansatz reaches such level of complexity that we don't know, or we cannot expand the ansatz. For example, at 5 loops, n equals 8 supergravity, we try to find these numerators, but you know, the ansatz can reach a million terms, and that's just an ansatz which has similar properties to an ansatz at lower loops, right? You know, you can try to write down an ansatz which is much worse. Sorry about this. And yeah, it just gets complicated. So that's really the problem at higher loops. And yeah, sorry about fiddling with my microphone. Any other questions? Yeah. Now this is an integrand level operation. It doesn't mean that there's any relation between the UV divergences of the two series. In some cases there are, but that's just because there's accidental properties that the numerator actually does not depend on L. So if one of the numerators does not depend on L, then it's very much like a color factor from the point of view of the integration, and then you can map the UV divergences. But in general, you know, it's unclear what the UV properties, you know, if they're related in any way. I mean, most likely they're not. Also, it's known that at 2-loop 5-point, the space of functions that you get is different, right? So yeah, it's not even, you know, in terms of writing this using integration by parts identities in a functional basis, they're different. But you know, they're similar, but they're different. And Lance is the expert in this.
But in the maximal case, they do have the same critical dimension until 5 loops.
Yes, until 5 loops, yeah. But the coefficients are unrelated, I would say, yeah. Right. Maybe, I don't know if there was one quick question, maybe there, yeah. 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 It's shifting L. You can. So I can shift. Yeah, I mean, you can say that. Well, you know, I mean, one obvious ambiguity here is which L should I use. So you can say that. Well, that's only a finite number of ambiguities. But it turns out that if once you do Jacobi relations, you get more general shifts. So you can actually check that the shift that you get here of L is basically it's basically a lattice which is made out of the external momenta, right? So any of the external momenta times an integer, you're gonna get from the Jacobi relation. So that's, you know, just an infinite lattice, and yeah, you don't want to try to deal with that, I guess. Yeah. All right. Maybe I just put it like this. All right. I think I have to move on. Sure. After integration? Yeah, that's what I was trying to answer or comment on. So there are similarities of the function space, but in general, the functions are different. The function space have overlap, but the function space is not the same. Yeah, so the function space is different, so there's no... After integration? Well, I mean, there are obviously IBP relations, and whether some of those can be inherited from Jacobi relations, I don't know. I mean, in general, I would expect not. Maybe some accidental identities, but yeah. All right, so let's talk about KLT. So this is Kawai. Level and Thai, and you already heard about it partly in Shruti's talk, partly yesterday. In fact, I realized there's many experts in the audience, so sorry for going slow. But hopefully I'm covering it in a slightly non-standard way, so it's hopefully interesting. So let's start from the double copy formula that I have up there, but just go back to tree level. So at tree level, we have a sum over 2n minus 5 double factorial diagrams. We have ni twiddle over di. So that's the double copy that we argued gives gravitational amplitude, if the input are gauge theory amplitudes. But let's try to massage this formula a bit. So I already told you that you can go to a basis. This is not a basis of numerators. So you can go to a basis of n minus 2 factorial numerators. So let's do that. So let's introduce permutations sigma and rho, which are permutations of Sn minus 2. And then we had this notation where we fixed two legs. So let's fix it to be 1, sigma, and n. And then we have this propagator matrix, or sometimes called Biajon scalar matrix, and n twiddle 1, rho, n. Right. So that's just a trivial application of the things I told you last two lectures. Yeah, so this is going to the n minus 2 factorial basis of numerators. And these are the half-ladder numerators, right? Now, one thing to realize here is that you might recognize that what I have here, this product, is actually a partial amplitude. This is what we called A1 sigma, 1 rho, because rho is the free index here, n, right? So that's what we defined to be a partial amplitude in the last few lectures. But obviously I can do it the other way around as well. So I can define this to be a partial amplitude. So let's call it A twiddle 1 sigma n. Okay, so it's interesting that in this formula we see that there's two partial amplitudes entering, but we can't quite write them out because they share this common matrix here, right? So essentially what we have to do is we have to put in an identity operator here. So roughly speaking, we want to put in a 1 which looks something like m and then m, let me not write out the indices, minus 1, right? So if we look at this matrix, we can try to find something like m and then inverse m, and maybe I should have written it the other way around. If you insert this thing here, then we get another copy of this m, and we can try to find isolate the partial amplitude. But of course, this is problematic, and the reason why this is problematic is because we already told yesterday, or said yesterday, that this matrix is degenerate, so it does not have an inverse. But nevertheless, we can try to do something like a pseudo-inverse. And the right way to do that is to go to the n-3 factorial basis of partial amplitudes, which is what you get from implementing the BCA amplitude relations. Okay, so now we again get the sum over sigma and rho, but these are now elements of Sn-3. And so we're gonna get, let me pick it to be this, sigma n, well, maybe I should call it rho for consistency up there. So rho, sorry, n-1 and n. So what I did here is I fixed one more leg. I'm gonna fix n-1 to be in this position. And then for my other amplitude, this one here, I'm gonna fix it slightly differently. So I'm gonna fix also the last two positions, but I'm gonna permute them. And I can do that because in the n-2 factorial basis, I can pick any two legs here. So I just made a different choice compared to the standard one, and then I fixed this guy to be there. You could have done it. You could have done it the same way as here, and then you would have gotten like a more symmetric formula. But this is actually a better way of doing it. And now I need a matrix here to join these two indices, and that matrix must have something to do with the inverse of this guy. So this matrix is what we call the Klt kernel. Now I mixed up the indices wrong. No, that's right, rho sigma. Yeah, so this is the Klt kernel. Right. And it's clear that you can do this because we know that there is a basis of amplitudes, which is n-3 factorial. And so you have to be able to rewrite your objects here like that. Might take a little bit of thinking how to do it. And yeah, so this S here, S of rho sigma, has to be some pseudo inverse of M, meaning that if I compute S rho sigma and sum over, yeah, so I multiply them together, M, like this. Sorry, not rho. What should I call that? Lambda, maybe. This has to be some Kronecker delta rho lambda in terms of permutations. Now, I put pseudo-inverse in quotations here because, well, the matrices are actually different size. So in order for this to work, you have to restrict, well, you have to extend one of the matrices or you have to restrict it. But subject to the fact that the range here is the same, which I think we should pick it to be S, probably n-3. Then you should get an equation like this. Anyhow, let me actually write down a closed formula. So there's a closed formula for S, the Klt kernel. So let me do it. So here it's a product I equals to 2 up to n-2 then it's the dot product of momenta, P1, and then P of rho I plus sum over J from 2 to I, and the dot product of momenta again, P rho I dot P rho J. This a coefficient here which is either 0 or 1, so I'm going to call it theta of sigma rho I rho J. That's it. So theta of sigma is just plus, is either 1 or 0, depending on the permutation. So it's 1 if when you plug in the permutation rho I into sigma, you get a larger number than when you plug it in Pj, right? Yeah, see, these are permutations. You can insert one permutation into the other, right? Otherwise, it's 0. Yeah, so it's a fairly simple formula. Modulo, you have to keep track of whether things are 0 or 1. There's also some recursive formulas for this. You can also compute it from some inverse of this object, although you don't get maybe the full, well, that, you know, there's an extended version of the Klt formula which you can just take this to be for any particle n. Also, for some interesting reason, this object here is actually harder to compute, or it's harder to get a closed formula for it. So here we have a closed formula. All right, so I'm going to show some examples. So the 3-point amplitude, we already saw that in Yara's lecture a few days ago. So it's just a product of two 3-point amplitudes. And I think I have to apologize for maybe messing up some sign somewhere. But for good measure, let me put in a coupling constant, which I didn't do there, but let's put in a coupling constant. So if you have a coupling kappa, which is the dimensionful coupling, we would expect it to enter like this typically. Well, depends exactly on your convention, but this is commonly chosen convention. For a 4-point, you get kappa over 2 squared, and then you have S12, A, 1, 2, 3, 4, and then you have a permuted ordering here, so you have 1, 2, 4, 3. And let me also write down the 5-point, and then I'm going to give up. So then it's a coupling to the 3rd power, and then you have S12, S4, 5, A1, 2, 3, 4, 5. Sorry for dropping the commas here. 1, 3, 5, 4, 2, and there's one more term. S12, sorry, S14, S25, A14, 3, 2, 5. Okay, the last one is 1, 3, 5, 2, 4. All right, and Sij here are just the generalized Mandelstam invariants, so it's pi plus pj squared. That's what it is in the massless case. You can also write this as 2 pi dot pj. And it turns out that that object is also true in the massive case, the dot product. All right, so yeah, so the basis is one-dimensional here, it's one-dimensional here, it's two-dimensional here, and that's why you see two terms, right? So that's what the n minus 3 factorial basis is, and so on. All right, any questions about the Klt formula? So this is a very explicit formula which writes, which relates gauge theory and gravity using gauge invariant quantities. So this is now gauge invariant. The problem with a gauge invariant formula is that it's overcounting poles. So you can see that this S12 factor is actually canceling out the overcount. So there's both S12 pole here and an S12 pole here. So this is just canceling out the double counting of the poles. Similarly here, there's some double counting of poles. This S factors cancel that out. So while you gained manifest gauge invariance, what you lost is the manifest pole structure, also manifest crossing symmetry, permutation symmetry of the external legs. It's much more obscure here. But you also get more compact formulas. All right, question? Here? It's just that it gives you a simpler formula. In particular, it makes this S local. So you see here, S here is just a polynomial. Well, it's a polynomial, right? If I didn't change this ordering, what would happen is that I would square the first amplitude, right? And then you not only have an overcounting in the S pole, but also in the T pole. So you have to multiply by ST, but that's actually the wrong dimension, so you have to then divide by U, because U would be missing, right? So if you pick the same ordering, you get non-local Klt kernel. It's possible, because I probably just copied it from, so there's an old paper by Svi. Were you on that paper? Yeah, Svi and Lance. Yeah. So maybe I should say something about history. So Quailova and Antai, they wrote their famous paper in 1986, and they were not considering field theory. They were, of course, considering string theory. So all of these formulas that I have here have a string theory uplift, which is alpha prime dependent. But I think what Klt did not do, didn't write down an explicit all n formula. They just said you can do it. So the explicit all n formula was written down later on by paper by Lance and Svi and company. And I think this is what I copied here. I think this formula has probably been the same for a very long time. But there's many ways of doing this, because there's this, you can make these basis changes. Basically you can fix any three legs as you like. That's a basis. And then after that, you can also use various identities. And so, yeah, I probably used a strange basis here. Yeah, I guess the issue is the 2 here, maybe, right? I think the 4 is fine here, but no. I think the I didn't want to write. I mean, the point here is not to be precise and write down exactly what this gives. The point here is just to illustrate that it looks like this. And if you're ever in doubt, what are the precise partial amplitudes and coefficients here? One way to check is to just check, is this formula crossing symmetric or not? I mean, it's not manifestly crossing symmetric, so only if you have the coefficients correct will you get a gravitational amplitudes where you have proper Bose symmetry, right? So here Bose symmetry is not manifest. If you write on the wrong thing, it's not going to be Bose symmetric. So, yeah. All right, any other questions? Yeah.
It looks like the M signal, like compose the propagator structure.
Yes.
So then, what's the information being encoded in the Klt?
What's the information? You mean what's the physical interpretation of it?
Yeah.
I don't know. So it has a recursive formula. I think the recursive formula maybe is more obvious to interpret in some way, but I don't know if anybody has interpreted it.
It's supposed to kill too many propagators in the
Yeah. But I mean, is there some simple way of phrasing it? Like, could you phrase like a simple problem which has the solution of the Klt kernel, which would not go via this, you know? It's some like mathematical or combinatorical argument. I don't know. Yeah. Yeah. Maybe. Yeah. So the M matrix has a much more obvious physical interpretation, which I will come to shortly. All right. So yeah. So I'm going to talk about some states. And I think I'm actually doing pretty poorly on time, so hopefully I will do this fairly quick. So let's consider the states that we get from doing Yang-Mills times Yang-Mills double copy. So I'm going to indicate the double copy by tensor product, which I think I also did yesterday. So obviously there's a graviton in the spectrum, h mu nu. And we can get a polarization tensor for the graviton by taking a product of polarization vectors for the gluon. Now you have to be careful. There should also be some little group indices. So here I'm in D dimension. So I have to introduce some little group indices. So my polarization vectors carries a SOD minus 2 index. So I is 1 up to D minus 2. So this is basically SOD minus 2 little group. Right, and, sorry, so this is different J. So this has 2 indices. And furthermore, it should be symmetric, so I have to symmetrize these indices. It should also be traceless. Let me indicate that by a double bracket. So that's symmetric traceless. Then there's also a 2 form in general dimension, which we typically call B mu nu. So let me write it down here. So this is also, it looks more or less the same. Let me put a twiddle to make it look different. Yeah, so now we have to antisymmetrize. So a 2 form is supposed to be antisymmetric, so that I just put the square brackets, that means antisymmetrization. Lastly, there's a dilaton scalar. Phi. This also has a polarization tensor in this way of thinking about it, but it has no little group indices. So this is just epsilon mu, where we have now contracted ij with a Kronecker delta. You can also put a normalization factor. One way of doing it is d minus 2. It's not quite canonical normalization, but that's one way of doing it. What's interesting here is counting the number of states. Let me put it underneath here. So it's a traceless symmetric tensor that's going to be d minus 1, d minus 2 over 2. That's a symmetric tensor. We have to subtract the trace. This is antisymmetric, so this is d minus 3, d minus 2 over 2. A dilaton is just 1. And if you sum up those numbers, so if you sum them up, this is going to become d minus 2 squared. And that's a feature of the double copy, that you get the squared. So d minus 2 is the number of states in d-dimensional Young-Mills, so we get the squared number of states, but it decomposes like that. Now, I guess I should do the same thing in 4 dimensions, because maybe that's a more interesting case. So in 4 dimensions, we have polarizations labeled by helicity, so we can form this state and this state, and these are the 2 polarizations of the graviton. So this is graviton, helicities, and there's 2 of them. Next, we can also form products between plus and minus helicity. So that's epsilon plus mu, epsilon minus mu, and we can add and subtract the corresponding flipped version. So just flip plus and minus. So that is the dilaton and axion scalars. So we have a scalar here, whereas we had a 2 form here, but in 4 dimensions you can dualize a 2 form to a scalar. So this axion here, let's call this phi, and let's call this chi. This axion is just a dualized b mu. And the plus sign is the dilaton, and the minus sign is the axion. Axion is a pseudo scalar, whereas this is a proper scalar. And if you're wondering, it's not exactly the QCD axion. It has similar properties, but this is a massless. This is a massless scalar. QCD axion should not be massless, I guess. All right. If you're interested, I could also write down what is the precise theory that this corresponds to, which I think I have time to do. So let me do that here, first for Young-Mills, or first in 4 dimensions. So in 4 dimensions, this is, so the Lagrangian is square root of minus g, because it's gravity. Then there's 1/2 Ricci scalar, so this is just the Einstein-Hilbert term, and then there is some contribution from this axion dilaton, and it's actually convenient to just label it. It's convenient to just call them. It's convenient to think of it as a complex scalar. So I guess we're going to call this one here tau, and then this guy is a complex conjugate, so tau bar. And then you can write down how they interact. So they interact with this following nonlinear interaction: d mu tau bar over imaginary tau. So it's nonlinear because tau appears in the denominator. And tau, in terms of these guys, we have I e to the minus phi plus chi. And if you expand phi to linear order and forget about the constant terms, then basically you have this identification that I did here. But yeah, this is the Lagrangian where you couple axion dilaton to gravity that the double copy actually gives. And maybe one more comment here is that since this scalar is complex, it can only be pair produced in interactions, which means that at tree level it cannot form unless it sits as one of the external states. And at loop level it can only form in closed loops. So that means that there's actually a procedure to get rid of it. So at tree level the procedure is just to drop it by not charging it. At loop level there's a subtraction that you can do from the double copy point of view that also gets rid of it. If you want, I could also write down a d-dimensional version, but maybe I should not. Yeah, I think I have a few more minutes, right? Yeah, so I also wanted to list some interesting theories. So Shruti already did part of my work. But let me list a few more interesting cases. All right, so I'm just going to go give some laundry list here of interesting theories that have either been proven or confirmed or checked to some degree that they satisfy color-kinematics duality. And when I say that, I typically mean tree level because there's no complete proof of loop level color-kinematics duality, well, except in one case, which I will mention at the very end, maybe. So n equals 4 super Yang-Mills, I think that's already been clear from previous lectures that does satisfy color-kinematics duality. And we know that this is related to Yang-Mills by Susy-Ward identities at tree level. So, you know, you can either take the perspective that if you know Yang-Mills satisfies color-kinematics duality at tree level, you know that n equals 4 super Yang-Mills does it, or vice versa. Using supersymmetry Ward identities. And of course, if you have n equals 4 working, you can do a supersymmetric truncation and get less supersymmetries. You can get n equals 1 and n equals 2 super Yang-Mills. So this is related to n equals 4 super Yang-Mills by truncation. So it is a consistent truncation, meaning that if you don't source your hypermultiplets or chiral multiplets, then they're not going to be produced at tree level. You can also do Yang-Mills coupled to scalar. I'm not going to write out the Lagrangian. I can say that it's actually related to Yang-Mills by dimensional reduction. So if you know that Yang-Mills satisfies color-kinematics duality in d dimensions, you can do a dimensional reduction and you get scalar. Now you can deform this theory by introducing a trilinear coupling. So that I typically called Yang-Mills plus phi cube, because that just indicates that there are two different couplings. There's one coupling for Yang-Mills and one coupling for phi cube self-interactions. Sometimes, you can also call this one Yang-Mills plus Bayer-Jones scalar theory, or sometimes it's just called Yang-Mills scalar theory, depending on which author you're talking about. And something I didn't have time to explain is that this bi-adjoint scalar theory is just the theory that gives the propagator matrix M. Then, yeah, there's a nonlinear sigma model. And I think Shruti already mentioned that. So this can be related to Yang-Mills by spontaneous symmetry breaking. So if you consider super Yang-Mills and consider spontaneous symmetry breaking, there's longitudinal modes which are related to the pions in the nonlinear sigma model. So from that point of view, maybe it's not so surprising. Okay, I haven't said that SSB works, but yeah, it's also true that spontaneous symmetry broke, yes, Yang-Mills, which is spontaneously broken on the Coulomb branch. Can never spell Coulomb for some reason. So if you take n equals 4 super Yang-Mills on the Coulomb branch, that also works. You can also do Yang-Mills plus fundamental matter. Which is basically some version of QCD. I'm just going to write this word. I'm not going to find what it is. There's something called Z theory, which comes from string theory. I'm not going to define what it is. Those of you who know what it is know it. Those who don't, I cannot explain what it is. It has an infinite tower of alpha prime corrections, and it satisfies color-kinematics duality, and also it works for Klt in the field theory sense. So I'm not talking about Klt as it was originally formulated by Kawai-Llewellyn and Tai. Yeah, so that also, so I could put open and closed string here, but it's a bit subtle, so I'm not going to discuss it. So that's also higher derivative. Higher derivative corrections to Yang-Mills, super Yang-Mills. But the last theory I'm going to mention here is Chern-Simons theory. And so here I actually mean just pure Chern-Simons theory without any matter. It was only recently realized in a paper by Maur, who's in the audience, that this actually satisfies color-kinematics duality manifestly from the Lagrangian, not just at tree level, but also at loop level, including all the Faraday-Post and so on. So that's the only example where color-kinematics duality is proven to any loop order, because it's just manifest from the Lagrangian in Lorentz gauge, I should say. This is Lorentz gauge. However, it doesn't have any amplitudes, so that's why people haven't really looked at it. It hasn't have amplitudes, so it's a bit trivial from that point of view. Do you have 2 more minutes?
2, yeah.
Yeah. Let's also say something about double copy theories. So the most obvious one is to do some supersymmetric. So let's say that I have P supersymmetries in super Yang-Mills, and then I have Q supersymmetries in the other copy. So this is going to give n equals to P plus Q sugra. Now it's only pure if one of these factors is a 4. So only pure if P or Q is equal to 4. The maximal case. Otherwise, if it's not maximal, you're going to get some additional matter multiplets, but it's still a supergravity with that amount of supersymmetry. You could do Yang-Mills plus scalar times Yang-Mills. what that gives is gravity coupled to Maxwell, sometimes just called Einstein-Maxwell. You can do Yang-Mills coupled to this phi cube interaction. So now there's a self-interaction. So that's just the non-abelian version of the one above. So this is GR plus Yang-Mills, which we often called Einstein-Yang-Mills. Then we saw a table in Shruti's talk about the nonlinear sigma-model, double copy, the bi-adjoint scalar, and Yang-Mills scalar. So I'm not going to cover that. Also, there's some stuff you can do here with string theory and higher derivative Yang-Mills correction, but I think I'm not going to cover that. Maybe the last thing I'm going to say is what is the double copy to get pure GR? So pure GR. So that has a double copy, which is essentially massless QCD times another version of massless QCD. Here you have to conjugate the massless quarks. So you have basically Weyl fermions. So you just conjugate them to the other one. And then lastly, I'm not sure if you can read it, but lastly you take the number of fermions, so a number of fermions or quarks to be minus, well, I'm not sure if you can read it. You take the number of fermions, NF, to be -1. So that remarkably gives the right answer. Now I should say that has been checked 1 loop and 2 loop partially. And there's some general arguments why this is the right thing to do. Also, when you supersymmetrize this, you can also ask about pure supergravities. And this seems to be the right prescription. So essentially, you introduce some extra quark, anti-quark, which when you double copy them form an axion-dilaton pair, which you can use to cancel out the other axion-dilaton pair. All right, I think that's it. So thanks.
Okay, thank you. Any quick questions before the break? Okay, well, if not, thanks, Henrik, for the whole course again. Okay, and we have a break. We reconvene at 12.